6.3 stars and planets. This is the review sheet. We're going to start right up in the left-hand corner. It says, what do these words mean? So an astronomical unit is the average distance between the sun and the earth. Okay, you don't need to know this. You just need to know it's the average distance between the sun and the earth. It's a distance. But it is 1.5 times 10 to the power 11 meters. So that is 1, 5, and then 10 zeros after that, because we always take it after the decimal. What is a light year? This is a really common question in an exam. It's the distance, even though that's year and you think it's time. It's actually the distance travelled by light in 1 year. And when you think of the speed of light, it's 3 times 10 to the power 8 meters per second. That's quite a distance, okay? And then we'll come to the next box down. Oops, I accidentally drew on that then. But it says there, two stars are 60 light years away from each other. So how long does it take light from one star to reach the other? Well, it's going to be 60 years. That's how long it would take. This is 60 light years. Light travels at 300,000 kilometers per second. Light from the sun takes 500 seconds to reach Earth. Use the equation distance equals speed times time to calculate the distance in kilometers. So I've put that into a triangle because I absolutely love triangles. I think they're very beneficial at finding what you want and rearranging. But the equation is kind of given to you anyway. So distance equals speed times time, because I'm looking for distance. So I put my finger over D, and then it's S times T. And then you've got 300,000 times 500, because I'm just replacing the values of the speed and the time, 500 seconds there. So I said it's 1.5 times 10 to the power 8, which is 8 zeros after the, or actually be 7 zeros after the 5 there, because the decimal's there. And that's in kilometers, which they wanted me to give the answer, but because I could as well, I added 3 digits there because we're going to take it from kilometers to meters. Remember, be smart, mate, stop being dumb. So if I'm going from big to small, I would divide and then I'd get more. Let's go for these ones then. Name all 8 planets and identify all the rocky and gaseous ones. So I've got here, my very easy method just speeds up naming, and then we'd usually say planets there. But Pluto is no longer classed as a planet, sad times. And we've got Mercury, Venus, Earth, Mars. These are the 4 inner rocky planets. They're generally smaller than the gas planets. So Jupiter, Saturn, Uranus, and Neptune are the gas planets. And in between these lie the asteroid belt, which is this question now. Between Mars and Jupiter, it's the last rocky planet and the first gassy planet. And there's a reason for that, because the gravity at this point, if you think of the sun being up by here, okay, and then you've got Mercury, Venus, Earth, Mars, and then the gravity gets less here, so it doesn't actually pull it together into a planet. They're just sort of loose pieces of rock, and then you've got these gassy planets on the outer skirts of the solar system. Let's go for the bottom one before we nip it back up, because that's to do with stars. It says here, how did the solar system form? Well, you got dense hydrogen-rich clouds of gas and dust. So the clouds of gas and dust is always going to be your top answer when it's asking for something forming in the solar system, whether it's to do with stars or planets or the solar system itself. So you got, and it's important we put hydrogen rich because that's how stars are going to form. And these are going to contract, get smaller under gravity. As the dust and gas is compressed, as they get smaller, the temperature is going to increase and the gas and dust is going to start to spin. And that's how you've got your solar system or your galaxy or whatever we're dealing with in space. I'm going to come back to the HR diagram because we need to know about the life cycle of stars first. Oh, I've just drawn there as well. Okay, let's zoom in on this bit. Name the main features of our solar system. So we've got 8 planets orbiting the sun. I've also put a star there. These take elliptical orbits, which is not a circle, it's slightly elongated circle. And we call those ellipses. Let me just zoom back out a minute so I can see all of the text. There's 4 rock and 4 gas. We also have comets, we have meteors. Be careful on your spelling of meteor there, because I spelt it with an I first and then I realised I was wrong. And asteroids, along with moons and other bits of cosmic debris. I also kind of forgot to put in dwarf planets there, but it's okay because Next question says, what makes up our universe? And I've said, well, you've got planets, stars, dwarf planets, satellites, moons, dust and gas, asteroids, comets, meteors, debris, galaxies, nebulae, and black holes. Just want to point out here that moons are natural satellites of planets, and there's also artificial satellites that we send up to monitor weather and your sat-nav and your mobile phones and things like that. So you got natural moons, which are satellites, which are just your moons, and then you've got a natural satellite, or artificial satellites, I should say there. Then we're dealing with some more distances and units. So we got 1 AU, an astronomical unit, is considered to be around about 300,000 kilometers. So that's remember the distance from the sun to the Earth, an average distance, because we do, depending on our orbit and where we are, whether we're winter or summer, we do become slightly closer to the sun at points. I think we're actually slightly closer to the sun during winter. I know that sounds bizarre, but it's because the tilt of the axes that we get winter, not the closeness to the sun. And then you've got 1 AU is around about 8.3 light minutes. So it takes around about 8.3 minutes for sunlight to reach the Earth. How far is 6.5 AU? So we're looking for a distance, so it needs to be in kilometers. I've also done it to meters as well, just because I did. So I got 6.5 there, times the 300,000. It's going to be 1.95 times 10 to the power 6. And I've also worked it out there. In meters, I've just upped my zeros. And then how far is 0.7 AU? Well, 0.7 times your distance, and that's going to be that far. And I've also done it in standard form there as well. How many hours? Oh, I didn't actually do it in hours. Look, I missed that. So this might be one for you. So I've actually done it in seconds there. I've also done it in minutes. So you're going to have to divide by 60 there to get that into hours. So 150 times 8.3. That's all I've done there. I've taken my hours, 150 AUs, and then I've just used this, and then, so to convert that into hours, you would just divide that now by 60, and you get your answer. Let's go down now. I'm looking for time. Yeah, not too bad. Describe the life cycle of a star the same size as our sun. So a smaller star. You're going to start with a protostar, which is a cloud of gas and dust clumped together under gravity. Okay, they contract, and that's how you get your protostar. And then that turns into a main sequence star, which is what our star is at the moment. I think our star is 4.5 billion years into our star, and I think we've got another sort of 4.5 billion years left on it. So we're not doing bad, and it's happy at the moment. The forces are balanced, and it's fusing hydrogen into helium. So there's plenty of hydrogen available for it to convert to helium. Not convert, sorry, fuse. So fusing is the joining of atoms together, or joining of nuclei. Red giant then, when it starts to run out of hydrogen, it's going to start fusing helium into the heavier elements that we find on Earth and other planets. And then once all that runs out, so the forces are unbalanced there, so that red giant's going to get bigger. And we've got a little table to show this down here. And then it's going to finish off with a white dwarf. So I'm going to keep this fairly simple by here. And then the cycle of a large star. So you can get a large star and you get a really large star. And it really depends on how they land up. But this is a general cycle. The first two stages are the same, protostar, main sequence star. And it's very similar reactions and pressures. Forces, sorry. And then you got your supergiant, so red supergiant or super red giant, as sometimes they call it. And then that becomes a supernova. It actually explodes because it's so unstable at that point that it actually sort of spews its guts into space. And that's how we get the start of that's your basically your gas and your dust ready to start another solar system or a galaxy or another star. And that's where we pretty much get everything. I mean, we are all made of stardust. Everything is made within that super red giant there. And then if it's just a big star, a really big star, it becomes a neutron star. But if it's a really, really big star, it becomes a black hole. And that's where the neutrons actually get crushed as well. So they call it a neutron star because it collapses so much that the protons and the electrons actually get crushed and there's only neutrons available, so a neutron star. And then your black hole will just absolutely demolish everything because the mass of the star is just so huge. I've done a little table here now to show the reactions. So main sequence star, MSS, Turns your hydrogen into helium for your reactions. Temperature's hot. You know, I wouldn't put my hand in it, put it that way. And then your gravity is equal to your gas and radiation pressure. So it's really happy. And then you've got your red giants, or your super red giants. It fuses helium into heavy elements, so such as iron and copper and all those other elements that we see on the periodic table. This gets slightly cooler. Now, nowhere near to put your hand in. It's just cooler than the hot star. So it actually cools down slightly because of the surface temperature. But I should imagine the inner core is quite hot. And then your gravity is less now. That's why it gets bigger. So your gas and radiation pressure is just more than your gravity. So that's why it gets bigger. And then I've said neutron star here, but that could also be a white dwarf, and it could also be a black hole where there's no reaction because all the helium's ran out. This is incredibly hot, much hotter than your first star, and gravity is much more than the gas and radiation, because your gas and radiation are no more. So it's just gravity taking over there as forces. We're going to go back to the Hertzsprung-Russell diagram. So it says describe the trend there. I haven't really described the trend. I've just kind of told you what it is. Hertzsprung-Russell diagram shows the stars according to temperature and luminosity. I've put in brackets here brightness, but it's important not to mention it as brightness, because brightness is how bright something is relative to something else. Whereas luminosity, because these stars, I suppose the brightness of it depends on whether they're close or distant. And some distant stars are actually brighter than closer stars. So that's why we need to call it luminosity. Now, luminosity, the scale increases, and here's the thing here, the temperature actually decreases as you go further this way. I know it's really hard to see on this diagram, but when we actually come to study these, the temperature will actually decrease this way. So you've got these stars which follow the main sequence. These are really, really happy stars. That's why they're called the main sequence. It's kind of this negative correlation. I shouldn't use that word because that's a maths word. But so as X increases, Y is decreases at a proportional rate there, at a steady rate. You've got your red giants then, or your super red giants. You can see that these are actually cooler, but they are more luminous. So we can actually see these more than your normal stars. But then you come to the other stages then, and down around this area, you've got your neutron stars, your black holes, and your white dwarfs, where they're really, really hot, but really hard to spot because their luminosity isn't the best. Okay? So that's pretty much an overview of the Hertzsprung-Russell diagram. And I think I've covered every box now. And if I haven't, I would have to make another video. But I think I have. What causes a star to form? Hydrogen contract under gravity, pressure increases the temperature there. What causes a star to reach its final stages, runs out of hydrogen to become a red giant, and then runs out of helium. I hope this all fits in one video.